Hello and welcome to a review for the topic of mechanics of materials. My name is Samuel Latte, here to kind of help refresh and review some information that you may find yourself seeing on the FE exam when you take it. So to begin, kind of a brief intro into what mechanics of materials is in regards to how the FE goes about it. The mechanics of materials is a study of the relationship between the external loads applied to a body and the stress and strain caused by the internal loads within that same respective body. What the FE will do is it will utilize your understanding of this definition and look for you to further implement some learnings based off of it to calculate stress and strain in members such as beams, shafts, etc. And from there, you're able to utilize these calculations to determine shear and moment diagrams to determine, bending stress, torsion stress, whatever they might be looking for. And what they typically do is they utilize about 9 to 14 questions related to the subject of mechanics of materials. It could be more, could be less, but most of these questions involve areas of mechanics of materials, such as the calculation of said stress, strain, utilizing those to create shear and moment diagrams, or something else such as displacement or deformation that members may experience under load. So going into some of the principal stresses that you may run into, beginning with the axial or normal stress. And what this stress refers to is a stress induced by a normal force, a force normal to the surface in question. And what this may look like is if you have, say, a beam or a member, a force will be kind of either pulling on it away like it's depicted in this picture, and that will be subjected to a tension force, or reverse this arrow to receive a compression force where you're basically pushing inward on this member. And the strain that is related to any normal stress is typically just the elongation of this member or element relative to the normal force that's applied. And we're able to relate our axial stress or normal stress to the force applied divided by the cross-sectional area in question. So what you would do is just divide this normal force by the cross-sectional area of this cylinder. Moving on to the other kind of stress you may run into regarding shear stress. And shear stress essentially refers to the stress induced by a force parallel to the surface in question. So if you take this square, for example, a shear stress is going to run parallel to the respective side. And we're able to relate our shear stress to this parallel force divided by the cross-sectional area of this, the side of the square or whatever member you're looking at. And the strain due to shear stress, shear strain, is related to the change in angle at a particular point relative to the force applied. Moving on to a different kind of stress you may see yourself looking at in the FE exam is bending stress. And what bending stress is a stress resulted from the compression and tension force experienced by a member subjected to a bending or deflection induced by an external force. So in looking at this beam, we see that there is a force subjected to the center of it, causing it to bend inwards or deflect. And what this will do will create a tension force on the outside of the beam as it's expanding to compensate for this bending, and the inside of the beam will experience a compression force, basically sinking in on each other again to compensate for this bending force. And we see that our bending stress is related to the moment experienced by the member multiplied by the vertical distance away from the neutral axis multiplied by the vertical distance away from the neutral axis divided by the moment of inertia. And what this vertical distance away from the neutral axis refers to is, say if we have a rectangular beam, our neutral axis being the center of it, and say this is 1 meter. So we have 1 meter of total width. This vertical distance away from the neutral axis will just be essentially this depth divided by 2, or 0.5 meters. And then the moment of inertia is just the moment of inertia of the cross-sectional area. So for this rectangle, you would have to refer back to the FE reference handbook to look at and determine the moment of inertia for the respective member. But if it's something as simple as a square or a rectangle, it could just be related to BH cubed over 12. But what we most importantly see is that the moment, the magnitude of the moment experienced by the member is directly proportional to the bending stress. So the greater the moment, the greater the bending stress a member might see. Again, another kind of stress you may encounter in the FE exam is the torsional stress. And this is related to the kind of twisting motion or torque applied to a member. And here we're able to see that our torsional strain relates to the change in angle, a fixed point on a member that a member experiences under deformation. So we see that before our twisting or torque, we see this point deflects and rotates to this point, and our torsion strain is related to this change in angle from where this point started off and ended at. And we're able to see that our torsional strain is related to the torque applied multiplied by the length of the member divided by the modulus of rigidity, which is also multiplied by the polar moment of inertia. And our torsional stress is once again related to our torque applied multiplied by the radius of the cross section. So just simply the radius of the cylinder, if that's what's in question, again divided by the polar moment of inertia, which can be depicted as pi d to the 4th over 32 for a solid bar. So an important aspect to always know regarding mechanics of materials is how stress is related to strain. And a material's relationship between the stress applied to it to the elongation or strain it experiences is the material's Young modulus, and this only applies to a stress-strain relationship within the elastic deformation part of our stress-strain curve. Otherwise, we see that this linear relation breaks down over time within the uniform plastic deformation and the non-uniform plastic deformation zones. And essentially your part will not come back to its initial length. It'll be permanently deformed, and there will be some sort of offset in the initial length of the member. And again, the strain within the elastic deformation region will not deform the material, as this linear relation determined by Hooke's law applies. But again, going anywhere further after this elastic deformation area will result in permanent deformation of the material. So moving on to one of the most important concepts in mechanics of materials is the shear moment diagram. And what these diagrams do is graphically shows the forces and moment change across the length of a member. And beginning how to determine some of these graphs is based off of your free body diagram. Your shear graph will be determined by the active forces on a member. So say we look at this first one, for example, we see that there is a center load offset by the reactive loads at A and B being upwards vertical and our center load going downwards. So we see that force AY will be straight up at the top of the beam, or the beginning of the beam. Force BY will go straight up at the end of the beam. So our shear graph will begin with a shear load equal to the magnitude of AY at the beginning. And since there is no change in load up until our force P, there is no change in shear until force P. This difference will be the resulting difference between force P minus force A. Here we see that force P is greater than A, so it will create a negative shear down to this point. Again, there is no change in force or shear from P to B, so there is no change in our shear diagram, and force BY will result in our shear diagram resulting back in 0. This difference in P minus AY will equate to BY, and that again can be related to our sum of forces in the y direction. A plus B equals P, or A equals P minus B, or A equals P minus, or B equals P minus A. And our moment diagrams can be derived by taking the integral of the function seen here in our shear diagram. So here we say this is 1 Newton. Our integral of 1 Newton would just be 1x Newton, or just x Newton. And our beginning and end of our integrals would be the distances it travels. So the distance from A to P, say, is 5 meters. So what we will do is multiply this 1x Newton function from 5 to 0 and essentially just drop the 0, so we see that it will begin at 0 and go up to 1 times 5, or 5, this being our max moment. Again, we take the integral of whatever this value may be, and we will take this point from the end of the beam to the center, again whatever values they may be, and we will see that we will get a decrease in moment down to 0, where our forces will all equal out and our beam will be in equilibrium. And if we see a graph like this, again we will have force AY and force BY, which looks like they will be equal and opposite to each other, but with an applied moment in the center. So again, having a force AY going up, our shear gram will begin positive, no change in force up until BY, no change in shear diagram until BY, going down, resulting in a 0 shear force at the end of the beam. But we see that we have a center moment in the middle of the beam, and what this will do to our moment diagram is, again, we take the integral from A to B, which will result in this slope seen here on both sides of the moment. However, this negative moment will offset or adjust the center moment diagram. Again, going from 1 to 5 or whatever value this may be, subtracting the total value of this moment, going down to this value, and again writing up the slope to a total value of 0. And in the case of a distributed load, once again we determine our force reactions of AY and BY with a center force equal to the magnitude of this distributed load times the length. And we see that with a distributed load, our shear force is always changing, and what this will equate to is this distributed load multiplied by the distance to achieve its function. Again, with our shear diagram, starting off with our force reaction at A, and then with our negative distributed load equal to the negative slope, with again a force reaction at B that equals to 0. And what we just previously learned is that our moment diagram is equal to the derivative, or integral, excuse me, of our shear force diagram. So our integral of this negative W slope, or negative x, it will be negative x squared. So this value of this function of our moment diagram will equate to a x squared over 2 graph. So moving on into some review questions, and I apologize for having these values already present. It's just got to be a little difficult to adjust it. But say we're looking at a beam with the width of 50 centimeters and a depth of 100 centimeters, and it is subjected to the loading here shown below. We want to find the magnitude of moment that causes the max bending stress in the beam due to these applied loads, ignoring the self-weight. So how we would begin something like this is to find the reactions at AY and BY. So we know that our sum of forces in the y is equal to 0, which looking at this will be AY plus BY minus 8 kilonewtons minus 5 kilonewtons. But we have two unknowns and only one equation. Here we would take the moment at A to get our force BY solved by itself. So we see that our moment at A will equal to this 8 kilonewtons going clockwise, multiplied by the distance, which is 6 meters, minus BY, because it is the opposite direction of what we denoted as positive, which would be counterclockwise in this case, minus BY times its total distance, which is 10 meters, plus, as it's going in our positive clockwise direction, 5 kilonewtons times the total distance, which is 6 plus 4 plus 3, or 13 meters. Here we solve for BY, which equals to 11.3 kilonewtons. Plugging this back into our sum of forces in the y direction, we can equate our AY to equal 1.7 kilonewtons. And going back to the review we just had on our shear moment diagram, we see that AY will result in a 1.7 kilonewton shear force in our shear diagram with no change in force until we experience a 8 kilonewton downward force. So our difference between these two values will be 8 kilonewtons minus 1.7, resulting in a negative 6.3 shear force up until this point, with no change until we get to BY, where BY is equal to 11.3 kilonewtons. So 11.3 minus 6.7 is a positive 5. And then we run this value until another force is applied to the beam, which is a negative 5. So 5 minus 5 will bring our shear force diagram back to 0. And then looking at our moment diagram, we will see that the integral of 1.7 is 1.7x, spanning from 0 to 6. So we know we begin at 0, but our 1.5 multiplied by 6 will lead us to a value of 10.2 kilonewton meters at this point. And then we see that we have another run of negative 6.3. Take our integral, negative 6.3, running from essentially 4 to 0 from this point. So 6.3, negative 6.3 times 4, taking the difference between that value and our 10.2, will take us down to a negative 15 kilonewton meter moment. And lastly, we will see that we have a 5 kilonewton value in our shear diagram. Taking the integral from essentially 3 to 0 at this point will result in 5 times 3, or a positive 15, again giving us a 0 ending in our moment in shear diagrams. And then looking at our moment diagram, we know that either this peak or this peak is the max moment the member will experience. And we see that obviously a magnitude of 15 is greater than 10.2. And then looking at our bending stress equation, it is directly proportional to the moment. So we know that this higher value of 15 kilonewton meters will result in a greater bending stress than our 10.2. So kind of reviewing some parts of the stress strain diagram, which is, in my opinion, pretty critical in understanding the different aspects of it. This is asking, in the stress strain diagram, select all points that describe, select all the point A describes. So point A is essentially referring to this linear section in the stress strain diagram. So our options is the elastic behavior, the Young's modulus, the ultimate strength, necking behavior, or plastic behavior. So we know that the linear part of the stress strain diagram essentially right off the bat refers to Young's modulus. And what Young's modulus tells us is that you can stress or strain a member from this point to, say, this point, and then removing this stress induced to it, the deformation will go from, say, whatever value you had it to back down to 0 and not experience any plastic deformation. So we know that plastic behavior is not one of our answers, along with necking behavior not being one of those answers. Here, ultimate strength relates to point C, where it is the highest strength or stress the material will experience during the stress strain relation. So again, we know that is not it. And then we see the last answer to look at is the elastic behavior. And again, what Young's modulus basically tells us is that within this linear section or zone, it will experience a elastic behavior where you can strain it, stress it to any point in this region, and it will return back to its initial value. So we know that this value is also correct for this point. And then lastly, just looking at another stress calculation, this question is also asking, a clevis is used to connect a steel bracket with a block of wood. It is subject to a force of 15 kilonewtons with the bolt having a diameter of 20 millimeters. It's looking for the average shear stress in the bolt along point A due to this force P. So we know that the force, the bolt with the diameter of 20 millimeters is under a force of 15 kilonewtons. However, there being two bolts on each side, we can essentially divide our force experienced on each bolt, the force experienced on one bolt divided by 2 due to the fact that there is two separate bolts. So we divide our force experienced by 2, our 15 kilonewtons by 2, to result in a force of 7.5 kilonewtons experienced on one bolt, with bolt A being the one in question. So we also know that our shear stress is related to the stress it experiences over its cross-sectional area. And in order to determine the cross-sectional area of our bolt, we need to take the pi r squared value of our bolt, with our radius value being our diameter divided by 2 in meters, just to simplify things for now. So our diameter in meters is 20 times 10 to the negative 3, or 0.02 meters. Divide that by 2 to get 0.01 meters. Square that and multiply by pi, and you get 3.14 times 10 to the negative 4th meters squared. So looking back to our shear equation, we see again that our force divided by area is related to our shear stress, and we know that the force experienced by the bolt is 7.5 kilonewtons, or 7.5 times 10 to the 3 newtons. Divide that by 3.14 times 10 to the negative 4th meters squared, and we see that we will get a value that is extremely high, 23.8 megapascals, or most nearly 24 megapascals. So I hope this review kind of helped you guys understand mechanics and materials a little bit more. I would suggest or say that it's pretty important to understand the different kind of stresses, where they appear at, and especially understanding the stress strain diagram, and be able to kind of use it to your advantage to know how a material might react to different forces and different deformations.